Hello Stormwater designers, welcome back to Clear Creek Solutions hydrology education videos. This video we're going to go over snow rainfall and rainfall variance as a whole over the entire nation in the United States. If you haven't watched any of our previous videos in the series, we have 8 other hydrology education videos so far in the Hydrology 101 series, so check those out if you've got a chance. We also have a free guide for you called the Ultimate Hydrology Guide. You can find that in the description down below. It describes the different kinds of hydrology, ways for finding peak flow. It breaks it all down for you there in this guide. So check the description for that. It's 100% free. Clear Creek Solutions is a stormwater modeling and a software company with 60 plus years of experience. And we've developed wwhm 2012 for the counties of Western Washington and similar continuous simulation software packages for states along the West Coast and the entire country. So let's talk about snow precipitation. So we know about rainfall, right? When it rains on a certain area, we have different rain gauges. We went over the kinds of rain gauges, and that can calculate rainfall. Snow is a little more complicated. So snow on the ground is measured in terms of the depth of that snow on the ground, right? So if you see snowfall, it accumulates, a lot of the time if it's the right temperature, and it can be measured. Large depths of snow are measured with a snow stake, which is a graduated post that can be installed anywhere. And because of the variation in depth, measurement is not accurate enough for snowfall. So we can use snow stakes, but it's not really accurate enough for our uses as hydrologists. So the water equivalent is what we use, which is represented from water from melted down snow columns. So if you took a snow column, you melted all the snow down, and you found out how much water we got from that. That's kind of what we want to use for snow precipitation as opposed to taking a stake, because there's going to be variations in compaction and depth and how that snowfall is prepared as a wet or drier snow, right? So there's going to be a lot of variation. What we want to know is the water equivalent. So here's an example of a snow stake in a super snowy area. Okay, so it's kind of stuck in the ground, but as you can see, the depth of snow, it varies a lot in this location here, and it's not going to really be reliable for our purposes of determining the absolute precipitation there, and then of course modeling facilities based on that data and information. We want to know the water equivalent. So the water equivalent is measured by forcing a small tube into the snow, removing it, and weighing the tube to determine the weight of the snow's core. So a specific gravity of freshly fallen snow is roughly 0.1, meaning the water equivalent is 0.1 for each inch of depth. So that's a pretty convenient measurement. The specific gravity increases with time as snow falls on the ground. So as more snow falls, the more compact it gets. That specific gravity is going to increase of the snow. And this can reach up to 0.5 in heavy mountain snow. So if we're getting a lot of snow, a lot of wet snow, heavy snow on a mountain, and it compacts a lot, it reaches a large depth, that specific gravity can get all the way up to 0.5, and that's going to help us determine the water equivalent. So the density of snow is often used with specific gravity, and the snow area can be measured from the air using different instruments, different things that we have available. We can kind of determine that snow area. So that's how we determine snow precipitation. Now we're going to talk about precipitation variation and patterns in the United States. So precipitation patterns in the United States reflect several interacting influences. So in general, the precipitation decreases as latitude increases, and decreasing temperatures reduce the atmospheric moisture. So sort of in general, as it gets colder, the amount of precipitation is actually going to go down because there's less of that atmospheric moisture. If you think about the tropical areas, they actually get a lot of moisture and a lot of rainfall. And as you get north, yes, they do get snow, and in some areas such as Pacific Northwest, it can also be cold and rainy. But as you go north into the North America, such as Canada, it's just going to be very cold, not as much precipitation. An important control is the distance from the moisture source, and this can be seen in precipitation found along the coast and the Great Lakes. So you can see along the coast and the Great Lakes, there's going to be quite a bit of rainfall actually in those areas. So if we look at the map here, we can see that the average annual precipitation in inches is seen here. It's color-coded. As you can see, for most of the eastern part of the state, it's actually pretty uniform, with a little more precipitation occurring in the warmer areas in the south. And as we head west through the Great Plains areas, we get to see a significant dip here in the rainfall or in the precipitation. As we go north, a little less precipitation here. And then, of course, when we get into the southwest, there's really not a lot of precipitation, as it's not near many large bodies of water, and it's less near the systems in the Gulf of Mexico and the Atlantic Ocean. It's more of these landlocked areas here. And in most of Southern California, however, when we work up our way up to the coast in the Pacific Northwest, the rainfall increases significantly as it's right near the coast, and we get a lot of rainfall systems here. So you can see some of the dark purple occurs here in the Pacific Northwest along the coast and into the peninsula here. But if you look at the Colorado Rockies range that runs through here, some of the different mountain ranges that run through here, that's really a cutoff for precipitation, as it usually doesn't make it over that area. And then we got some patches here in Idaho and Colorado that do get quite a bit of rainfall. So it's interesting to look at that there. The importance of mountains as a factor in precipitation by orographic lifting is evident in the isohedral pattern in the western states and along Appalachia. So if we look back here, along Appalachia, maybe a little more rainfall in those areas. And then it says here, a pattern in the western states, right? When we saw we crossed over the mountain ranges, or in the mountain ranges, a little more precipitation in those more mountainous regions. And heavier precipitation normally occurs along the windward slope of a mountain range with a ranged shadow on the leeward slope. And then time variations in precipitation may be more important than some of the regional variations. So when and how it rains actually may be more important than sort of the regional divide of these areas, because we're also looking at sort of the peak flows that can occur from large rainfall events. So if we look here, some of the wettest places in the U.S. is just sort of another interesting graphic here. New York actually gets quite a bit of rainfall, and even in the summer, Washington State and Pacific Northwest gets plenty of rainfall in many areas in the south. These are all near large bodies such as Pacific Ocean, Gulf of Mexico, East Coast. We can see places through here that are more landlocked, not near those large water bodies, not really getting the same amount of precipitation there. Here's another interesting graphic here. We can see that through time in different months that the total precipitation percentiles can change drastically here. So we can see during some months that these areas are actually getting below average precipitation. Some areas are getting more precipitation. So the timing of that, as stated before, is also going to be really critical when it comes to precipitation. So variations in precipitation from year to year make it important to design our reservoirs or detention facilities, whatever we're using, that are adequate during years of low rainfall. So for reservoirs that are storing water, we want to make sure we have enough water that even during those low rainfall months, there's still plenty of water available. So reservoirs must carry water in storage for a period of several years, and over 100 different cycles in precipitation with periods up to 700 years in length have been reported by many. And also sunspots and planetary configurations have been among some of the factors suggested as controlling these precipitation cycles. So that's an overview of precipitation variation and snowfall in this lesson 9 here. If you have any questions, leave in a comment down below, and we'll see you guys in the next video.